Hi guys, I'm sorry I had to cancel the lecture this Tuesday, but since I think it's important that we complete the chapter on resource allocation, I'm recording this video instead. So let's get started. So the last part that we have to cover for the chapter is radio planning. What is radio planning? So basically, when we have to install a new wireless network or to extend an existing one into a new area, or we want to modify the characteristics of this network, we need to design the fixed and the radio parts of the network. This last phase is called radio planning, and it involves the deployment or the modification of the characteristics of the base stations installed for covering the area. So the basic decisions that must be taken during the radio planning phase are where to install base stations or access points depending on the technology, and how to configure base stations in terms of antenna type, height, sector orientation, tilt, maximum power, device capacity, and many others. So basically we have a number of points where we can install base stations, so we have to decide where we want to install these base stations. Of course, we also have points where we expect to have users in the area, and those are the points that must be covered and with enough capacity for the network. So when planning and optimizing a cellular system, a number of aspects must be considered, including the signal propagation, which is exactly the point that you covered during the lecture on the radio propagation tool with Mr. Delana. But also traffic estimation, antenna positioning, antenna configuration, and of course interference. So we will focus in this part on the decision problems that can give rise to interesting and challenging mathematical programming models, decision models, that can take into account the specific aspects of the network technology. So one of the key aspects for the radio planning is propagation, and that's exactly what we have been working on during the lecture with the tool. So the covered area is where we receive a signal strength which is above a threshold which make the quality of the signal good enough, and that's, as you know, is depending on the specific characteristics of the technology and the modulation and encoding scheme that we are using. So for the received signal strength, of course, we know that this depends on the path loss that we have between the transmitter and the receiver, and of course the interference that is depending on the other transmitters using the same spectrum portions. So traffic estimation, of course, is one of the critical aspects, right? And this is usually hard to predict in the case you have to install a new base station, because of course you have to figure out how much traffic you expect to cover, you expect to have in the area. It's a different story when you are expanding a network, because typically when you take a decision on adding new base stations in a network, you know very well why you are taking this decision, because you are measuring traffic and you are taking decisions based on the traffic that you measure. So traffic distribution is then somehow given and based on predictions or based on measurements. And in our models, we describe traffic using a set of discrete points. The reason why we use the discrete set, of course, is because it's much easier to have discrete optimization models instead of continuous ones. So these points that we want to cover, where we assume that traffic is concentrated, are called test points, TP. So the selection of possible antenna sites depends on several technical and non-technical characteristics, like traffic density, distribution, ground morphology, electromagnetic pollution, local authority rules, agreements with building owners, and so on. We denote the set S as the set of candidate sites. So a candidate site is a site where we assume we can, if we want, we can install a base station. Of course, the set of candidate sites may be, in the case we are expanding the network, sites where you already have a base station and we just want to modify the characteristics of this base station. So considering the set of candidate sites and the set of test points, then of course we can give also the propagation characteristics of our network, and this is through the channel gain Gij between test point I and candidate site J. This is exactly what we expect to get from a propagation prediction tool. So the antenna configuration, as you know, can consider a number of different aspects. Of course, in case you are installing a new base station, you can decide which base station you want to install, and then of course the radiation diagram of the potential antennas that you want to install on your base station is one of the characteristics that you want to take a decision on. In addition to these, of course, if you have, for example, sector antennas with 3 or more sectors, you want to decide the horizontal orientation of these antennas, and in most of the cases also the vertical orientation, which is known as tilt angle for the antenna. Usually you also have to take decisions on the maximum emission power that you want to have for the antenna. This is reflecting, of course, a number of constraints that you can have also in terms of the electromagnetic pollution that you have for the antenna. But sometimes the decision also depends on the area covered, but also on the interference that you may generate on the other base stations. Then, of course, the height of the antenna is one of the most important parameters. Of course, if you have the possibility to have a tall site where you install a base station, you will be able to cover a larger area. In case you are forced to use a much shorter site than with lower height, of course, then the area covered is smaller. And then of course you have the capacity of the base station. Of course, we studied the capacity of the base station in terms of the radio interface, but you may also have limitations in terms of the link connecting the base station to the rest of the network, which is known to be the backhauling link, and a number of other characteristics. Of course, if you include all these elements in your decision problem, then of course the number of potential combinations can be extremely large. But of course, you can restrict the set and then maybe refine the problem once you have defined the first planning of your network. So we will see some simplified models, but in general, you have to consider that this kind of decision are taken with different rounds, with the first design of the network and then some refinements that depends on the specific characteristics that you want to further optimize. So of course the antenna configuration affects only the signal level received at these points. So we have a candidate site J, and then we can define a set of possible antenna configurations that we call Kj. We can assume that the antenna gain is Gij, and it is between the test point I, the candidate site J's, and the configuration K of this candidate site. Based on signal quality requirement and channel gains, that we can evaluate if this point I can be covered by candidate site J with an antenna with configuration K. This is a way of basically translating all the characteristics of the channel into a 0-1 matrix, and this 0-1 matrix can be considered the coverage matrix of our planning problem. So we can define the coefficients Aij, which is equal to 1 if this point I can be covered by candidate site J with configuration K and 0 otherwise. So summarizing, we have our set S of candidate sites. We have for each of them we have a set Kj of configurations. Then we have the set of test points, the set I, and then we have our coverage matrix Aijk, which tells us if the test point I is covered by candidate site J with configuration K. So the goal of the coverage planning phase is to select where to install base stations and to select the antenna configurations in order to guarantee that the signal level in all test points is high enough to guarantee a good communication quality. Note that interference is not considered in this phase, and also capacity is not considered in this phase. Later on, we will try to extend also the models so that we can incorporate at least partially the interference and also the capacity. So the first very simple optimization model that can be used for our problem is the set covering problem. In this problem, the decision variables are yj, which are equal to 1 if a base station is installed in cardinal site j and 0 otherwise. For the first case, we are neglecting the aspects of configuration of base stations in candidate sites. So the propagation then is just given by this matrix Aij, where the coefficient is equal to 1 if candidate site j covers this point I and 0 otherwise. So the problem is to minimize the sum over j of cj yj. This is the total cost, and cj is the cost for installing a base station in candidate site j. So cj yj is the cost associated to the decision of installing a base station in candidate site j. If we sum over all possible candidate sites, considering the decision variables yj, of course, we have a total cost. So the constraint that we have is that all test points are covered. So this is the sum over j of aij yj that must be greater or equal 1. Of course, if a candidate site is installed in j and then test point I is covered by j, then this generic term of the summation is equal to 1. So in general, if we sum over all candidate sites j, then we have the number of base stations installed that cover test point I. So constraining this to be greater or equal 1, we are just constraining the problem to cover at least with one base station all test points. So if we define the set Pj as the set of test points for which the coefficient Aij is equal to 1, this is basically the coverage set of candidate site j. So the variables yj define a subset as star, which is a subset of the entire area that we want to cover, right? So in such a case, if we take the union of all the coverage sets associated with the decision vector y, then basically what we are asking the system, the problem is to have the union of this coverage set to be equal to the set of test points. So basically the idea is that we want to cover all possible test points with a number of coverage sets, Pj, such that the cost is minimized. So of course this is a problem that can be easily extended. So if we want to incorporate the configurations, then basically we need to extend the definition of the decision variables. So yjk equal to 1 if a base station with configuration k is installed in candidate site j and 0 otherwise. And of course the installation cost can also incorporate the configuration, because of course you may have different costs depending on the configuration. So we have cjk, which is the cost associated to the installation of base station in candidate site j with configuration k. And this is the problem, which is just the extension of the previous one, and you can see here it's not much different. The objective function is just the total cost. Of course, now we have to sum over j and k, because we need to consider the possible configurations. The second one is exactly the same as before, so it's the full coverage constraint. So we for each test point we want to be sure that it is covered by at least one base station, and then we have one additional set of constraints, which is the summation over k of yjk that must be smaller or equal 1, and basically this is constraining the installation such that if you decide to install a base station in candidate site J, then you have to associate a maximum of 1 configuration to this base station. You cannot install more than 1 configuration in the same site. Of course, decision variables are binary variables. This class of problems is actually more general than the specific application that we are considering. These are known to be NP-hard problems. However, there are several efficient algorithms that have been proposed that can be used. And as we did for the frequency assignment problem for our exercises and our examples, so we can use a simple greedy algorithm that in general is actually even more efficient than the one that we have been stations that are installed. So we start from an empty set. Then of course we have a termination condition that of course is a termination condition that stops the algorithm when we don't have additional test points to cover. And then for each of the candidate sites that are where we didn't install base station yet, we select the one which has the ratio between the cardinality of the coverage set Pj and the cost Cj, which is maximum. Of course, we are ranking the candidate sites considering those that have this ratio as the largest as possible, and of course we are adding one by one this to the solution that we are building up with the greedy algorithm. So of course we select this candidate site k that is maximizing this ratio, and we add this to the solution set. Of course, in this case we are not considering configurations, but of course the extension is trivial. The important part that we have for the update before we iterate on the algorithm is that we delete from the problem all the test points that are already covered by the candidate side, the base station in K that we just installed. So basically we are deleting these points from the problem, and then of course we have new values, new sets Pj that we will use for the second iteration. So this is what we do step by step until we have these coverage sets Pj empty, which means that we have covered all test points, and then of course we stop. So let's see an example. So this is an example, a small one. The matrix V is the matrix of the coverage coefficients. So we have in the rows we have our candidate sites, and in the columns we have our test points. So in this case we have 1, 2, 3, 4, 5 candidate sites, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 test points. So the coverage set, the cardinality of the coverage set can be easily obtained just summing by row the number of ones that we have in the row, right? So in this vector pi, I'm just calculating these values that are the cardinalities of the sets Pj. For simplicity, in this example, we are assuming that the cost is equal to 1 for each candidate site. So in the end, the ratio between the coverage set cardinality and the cost is just equal to the cardinality of the set. Okay, so of course we start from the one with the highest number of test points covered, and of course this is the last one, the fifth one. Okay, so of course this is added to the solution, right? So we had this candidate site number 5 to the solution. Of course, this is covering all the test points that are marked with the orange box. As I mentioned before, we have to remove these test points from our problem. So basically, I have to put zeros corresponding to the columns of these test points, and this is what I do here, right? So I put all zeros here, and then of course, once I have put all zeros there, I can recalculate the cardinalities of the set Pj's for the other 4 candidate sites that we have to consider for the second iteration. Okay, so in the second iteration we have 2 candidate sites that cover 3 test points. So for simplicity we just follow the order. So in this case then we had the first one. So we had candidate site 1 to the solution, as you can see here, and we recalculate again the values of the cardinality of the sets. So again, we have to consider the test points, the 3 test points that are covered by candidate site 1, and then we put zeros in the corresponding columns. Okay, so we do the recalculation, and we now have the new values for the set Pj. Okay, in the column here. Now then we can move to the third step, which is this one here. In this case, of course, we are adding the candidate site number 2. This is covering 2 test points. Again, we recalculate everything for eliminating these 2 test points from the problem. Then we have just 1 remaining test point, so we just add the final candidate site, which is number 3, and then we recalculate everything. And as we see here, we have now an empty matrix and an empty vector pi. So basically this means that we don't have to cover any further test point, and this is the solution of the problem, that is using 4 out of 5 candidate sites for covering all the test points in the area. Of course, this is a solution that has been obtained with a greedy algorithm. In general, we cannot guarantee that this is optimal. In this specific case, you can easily spot, since the problem is small, you can easily spot that we have a better solution, which is the one that is obtained just with the first 3 candidate sites. And you can see here this is covering all the test points. So the optimal solution is actually using 3 out of 5 candidate sites, and our solution with the greedy algorithm actually is 4 base stations. Of course, the problem that we have been modeling is rather simplified. So and in particular, there are a number of cases in which the coverage of all the test points can be extremely critical. In particular, if some of the test points may be in very difficult propagation conditions. So sometimes the coverage requirement can be considered a soft constraint instead of an hard constraint. And for this reason, we can relax this constraint and add a penalty in the objective function, such that we try to cover all test points, but somehow we balance the coverage with the cost. In this example, we have here the objective function that incorporates variable zi that are indicating if a test point I is actually being covered, and then, as usual, the cost. So we maximize the coverage, but we then balance this with the cost. So we have a coefficient, trade-off coefficient lambda multiplying the sum of zi minus the sum over j and over k, of Cjk yjk, which is the total cost. So this is an classical objective function where we have actually two objectives. One is the coverage, the other one is the cost, and we are balancing between the two with a trade-off parameter lambda. So the constraints, of course, are basically the same. The only difference is that, of course, the coverage constraint now is requiring that the number of base stations covering a test point I is greater than or equal zi. Of course, if zi is equal to 1, then of course this is exactly equivalent to the previous case. But if zi is 0, of course, because we are not covering, we are deciding not to cover test point I, of course, then this is basically a constraint which is always satisfied. And the rest of the problem is the same. So in the models that we be using, the coverage constraint, both the hard one and the soft one, they just require that the test point is covered by at least one base station. But actually, the sum over j and k of ai jk yjk is actually giving us the number of base stations, the total number of base stations that are covering test point I. You can easily guess that in most of the cases, when you install your base stations, some of the test points, at least some of the test points, can be covered by more than one base station. And that's pretty normal also in real scenarios where you have the points of the service area of a radio network that are covered by more than one base station. The specific base station that is serving a test point is not specified, it's not defined by the problem, right? We are just asking that it's more than one. Of course, we can add one more variable to the problem such that we can take a decision also on this assignment. So given the set of base stations covering a test point I, we can decide to which a specific test point is assigned. So xij is equal to 1 if test point I is assigned to candidate site j and 0 otherwise. So this is exactly the same problem as before, with the only difference, of course, that we are using the variable x, the set of variable x, and of course we are rearranging the constraints in order to use this new variable. So as you can see here, the definition of variable x here is exactly the coverage constraint as before. We are using it as a definition of the variable in such a way that we can guarantee that, of course, we can assign the test point only to candidate sites where there are base stations installed and covering the test point. And that's, of course, an important constraint. Otherwise, we may be assigning a test point to a base station that is not covering it, right? The coverage constraint is just rearranged using the variable x, but of course, this is equivalent to the previous case. If we take a look at this problem, we can see, of course, that we have a new set of variables. However, these variables are not really adding any constraint to the solution that we build. For the moment, we are just taking a decision, and this decision of assignment of test points to base stations is arbitrary, given the set of base station covering test points. So the constraints that are really active in this problem are as before. So basically, we are free to assign test points to base stations, since this decision has no impact on the objective function. If we want to, and to this regard, of course, you may say that this formulation is useless in practice because we are adding a new set of variables without using them. If we want to use these variables, of course, we need to make some modifications. And one of the modifications that we can have is on capacity, right? So far we have been just modeling the coverage, but we didn't consider the capacity of a base station. And we know that this is an important parameter because the spectrum that is assigned to a base station is limited, and then the capacity that we use is limited also because of the coverage, right? But can be also limited by the backhauling link. So if we assign test points to base stations, we can consider also the capacity. So in this example that I'm showing you here, we are considering these coefficients, di, which is the traffic associated to a specific test point. So this traffic can be measured in Erlang or in bit per second if you wish. So the total capacity of the base station can be, of course, defined depending on the technology, depending on the specific characteristics of the base station. So let's assume that we also have this information, which is recorded in this set of parameters Vjk. So Vjk is the capacity of a base station in candidate site J that is configured with configuration K, right? So then, and of course we assume this capacity is the same unit of the traffic here, right? So with this constraint, we are just saying that the total traffic that we assign to a specific base station, which is just given by the sum of the traffic of the test points that are assigned to that base station, must be smaller or equal the capacity of that specific base station. And that's exactly what we have in this constraint. So this capacity constraint, of course, if we had this constraint to the previous model, of course, in this case, we do use the variables x, and this, of course, can reshape the problem in a way that includes also these additional capacity constraints. In the definition of the variables x, we assume that, of course, we can arbitrarily define this assignment selecting one of the base stations that are covering a specific test point. This is not necessarily what can actually happen in a real network, because, as you know, typically the cell selection is a procedure that is done by the mobile terminal, considering the signal strength of the base station in the neighborhood. So basically, if we try to mimic in the model this cell selection process done by the terminals, we should be assigning a test point to the base station that is received with the highest signal, right? So basically, depending on the propagation, depending on the emitted power, of course, we basically have a ranking. For each test point, we have a ranking of the base stations received from the highest to the lowest signal strength. Of course, this is done on the candidate sites, and when we define this ranking, which is given by this vector here, where we have the candidate site and of course also the configuration that of course has an impact on the signal strength. When we define this vector here, of course we don't know which base stations will be actually installed by the decision model, right? So we have a ranking, and in order to force the assignment with variables x to the first one in this vector, that is the first in the vector where we do install base station in our decision model, we can use this set of constraints. So this set of constraints is basically used for forcing the decision on variables x. So as you can see here, this constraint is actually a set of constraints for each test point. So we have a number of constraints per test point. So this is for test point I in this example. So basically, if we follow the order, right? So basically, we follow the order from 1 to L, where we assume this is the length of the vector here. So of course, if the first candidate site is the one where we have the variable equal to 1, which means that we have installed the base station, then basically what we have here is that the sum of the other assignment variables will be forced to be 0, so which means that the only variable x that is allowed to be 1 is the first one. So we are assigning the test point to the first base station. If this is not the case, then of course we have the second constraint that can be used for the second candidate site in the vector, and of course the meaning is exactly the same. Otherwise, we have the third one and so on. So basically, using this set of constraints, we will be forced to assign the test point to the first installed base station according the ranking defined by this vector. This is a classical way of enforcing a sorting order in a decision variable in optimization models. Okay, so basically we have seen how we can use optimization models for modeling the decision on how to plan a radio network, how to modify the configuration of the radio network. These are models that are incorporated in most of the decision tools that are used by operators. Of course, these are just supporting tools that are used by operators for taking decisions. Then, of course, there are a number of practical aspects that cannot be captured by these tools. And then, of course, there is kind of manual refinement of the solution. But this is an interesting way of understanding how complex decisions can be taken, and you can imagine also that the sizes of the instances of this problem can be very big, involving tens or hundreds of base stations that must be installed. In a big city like Milan, you have hundreds of base stations installed, and you understand that sometimes even the capacity expansion can involve several tens of base stations. So we will be working a bit also on some numerical exercises that can be based on these problems, including also those based on the greedy algorithm that we just studied. Okay, thank you for your attention, and sorry again for canceling the lecture.